Hi, welcome to Mathematics with Tom. I am Tom, and today we are going to prove, or I'm going to prove for you, the Fundamental Theorem of Calculus, the second, part 2 of 2. And remember, the Fundamental Theorem of Calculus is a lot to write, so you'll often see it abbreviated FTC, Fundamental Theorem of Calculus. And here's what it states. It says, if f is continuous, if f is continuous on the closed interval from a to b and f of x is the antiderivative, meaning from a to x of f of x, f of t, let's use t, f of t dt, then here's the big piece. Then this integral, from the definite integral from a to b of f of t dt is equal to capital the antiderivative evaluated at b minus the antiderivative evaluated at a. So this proof, I think, actually is a little bit difficult, and here's why. Because we intuitively know something. For example, if I told you that f of x is x squared plus 2, then you could say that f prime of x is 2x. But watch, what if I gave you another function like this? Say I gave you the function g of x, and g of x is x squared plus 3. Let's do a 3. X squared plus 3. So f prime, not f, g. For g, I should write the correct letter. G of x, or g prime of x, is also 2x. So hold on a minute. Notice the derivatives are the same, but the functions are different, okay? So that's what's interesting here. So let's do this. So let's say this. What we know then is let's do this. Let g of x also equal the integral from a to x of f of t dt. Now, here's what we do know. We know then that their derivatives, the derivative of g and the derivative of f, are the same. So that's all we know. That's what we learned in the first part of the fundamental theorem of calculus. We know that if we take the derivative of capital F, we get lowercase f. If we take the derivative of capital G, we get lowercase f. So in other words, g prime of x, well, that's equal to f prime of x. And, well, if they're equal, then if I take g prime of x and I subtract from it f prime of x, well, we know that function, that's 0. And I'm going to call g prime of x minus h prime of x. Let's say that's just the derivative of some function. We'll call it h prime of x, okay? So we have some derivative that equals 0, and it just happens that that derivative is just the difference of two functions. And we know that if you can apply the derivative to over a sum, that's another proof that we've done. So let's take a look. So here, though, this is what's interesting. Here, we need the mean value theorem of derivatives for this one. So we need the mean value theorem. Mean value theorem, that's just all we need, and probably should have done a capital T. And in general, what this says is that it says, remember this, if you have some function, in this case, h of x, it says this, It says if h is continuous, on the interval from a to b and differentiable, and h is differentiable, on the open interval a to b, then there exists, and I don't know if you've ever seen, there's a symbol that's often used for that. It's this backwards capital block E, there exists. So we'll use it in the, let's use it now. There exists, you write like this, there exists some C in our interval from A to B, such that you can approximate it. In other words, if your function looks maybe like this, if this is your function h, then it has there's some point in this function that you could just make a secant from the point A to point, or h of A to h of B. So let me make a better picture here. Oops. So here's A, here's B. What it says is that there's some C, and you can see this one probably has 2. There's some C's where you could approximate that slope. There's one and there's one. Either of those 2 values would work as a C. So in other words, what you can say then is the mean value theorem says that the h of C is equal to the slope of that secant line, h of B minus the h of A, that's the rise over the run, which is B minus A. But wait a minute. Oh, h prime, the derivative is equal to just that slope equation, just using what we know about a simple line. But now look at what else we know. We know that h prime of C is equal to 0. Well, in order for this to be equal to 0, that means that the numerator has to be 0. So this implies that h of B is equal, I'll write this, that h of B minus h of A has to be 0. Well, that implies that h of B has to equal the h of A. Whoa! Well, what does that mean? That means we need a new screen to finish out what we're working on. So let's take that. Let's take what we've got, and we'll recreate some of these pieces here as we need them. Okay, so we're here. We said that the h of B is equal to h of A. Okay, well, remember what h of B is. H of B is G evaluated at B minus F evaluated at B. And h of A, well, h of A is G evaluated at A minus F evaluated at A. Okay, well, let's go back to what we said. We said that capital G, remember this, that capital G is the integral from A to B of f of t dt. And let's subtract the f of b, or add an f of b. So this is going to equal, well, the g of a, I'll just write this out, g of a plus, I'm going to put a parenthesis, here's my f of b, minus the f of a. Well, whoa, look at that. Let's go back. That is exactly this. That's what we were trying to prove. That's what we were trying to prove. Oops, sorry. There we go. There we go. Okay, here it is. That's what we were trying to show. We need this f of b minus the f of a. Well, let's go back. I think we can finish this. I think we've got everything we need. So I'm going to come back and look at where we are. So this is equal to the integral from a to b of f of t dt is equal to the integral, well, g of a is the integral from a to a of f of t dt, plus we have the f of b minus the f of a. Well, here's the kicker. The last piece is that if you were to integrate, let's take a quick look. We said our function looked something like this, and here was the point A. Well, if you integrate from A to A, what is the width? What is the width of that rectangle? It's 0. There is no width. There's no area under the curve. So in other words, this right here is 0. So I have, this is the integral from A to B of f of t dt, and I'm just going to write this so you can keep track. Well, that's just 0 plus f of b minus the f of a, and there's your answer. Because 0 adds nothing, so that's just f of b minus, f of b minus the f of a. And that is the proof of the second fundamental theorem of calculus. And in our next video, we're actually going to take some practice applying the entire fundamental theorem of calculus and how it can help in making calculations. I hope that helps. Thanks for watching.